This is going to be, so this is a talk on parallelism, okay? And I'm going to start out a little bit slower because I need to build my way up to it. But what we're going to talk about is we're going to talk about different methods of decomposing problems in YT into different parallel strategies. Okay? So some operations in YT are natively parallel. Some of those operations scale reasonably well. Some of them don't. And we'll talk about the differences between those. And I'll also show you some constructs in YT that can help with or harm your parallelism journey. In contrast to what we've done in previous, this talk is going to be much less notebook oriented. It is possible to do notebooks, to do this type of parallelism in notebooks, and it's probably easier than I remember. But for my Chris is shaking his head no. But for my purposes, I have a much easier time doing this on the command line. Okay, so I want to note that I have installed MPI for Pi. So I used Mamba. It's essentially this, the interface is the same as Conda, but my Conda installation is so complicated, I need a better snake called Mamba, which was like developed by, I forget the company's name, but it's like, a faster version of Conda. Does anyone here play Sudoku? So I learned a while ago, apparently Sudoku is isomorphic with dependency resolution. And you can implement a Sudoku solver just using Python dependency specifications so that if you pip install a particular package, it'll solve Sudoku, like actually Sudoku to do it. Anyway, Conda can be a little bit slower. You can also specify like use the Mamba solver. I know this is a little bit off topic, but I feel obliged to let you know that I am already starting with MPI for Pi installed. And I did that by doing, in my case, Mamba install, but you can do Conda install MPI for Pi. I don't recommend doing this through pip. You can do it through pip, I believe, but I recommend sticking with Conda simply because it will it tends to be what cluster managers utilize in my experience. And so it'll already be, it'll know how to integrate with your existing MPI installation on your cluster, which can provide considerable benefits. Or if you're on your own laptop, it will install an isolated version of OpenMPI. I think it does OpenMPI, not MVAPICH, that only works with your Conda stuff, okay? So all that being said, I'm going to take as written that you have installed MPI for Pi. MPI for Pi is a really cool library. It does some really neat stuff with the way that it exposes generic MPI constructs. So if you learn parallel programming, you can do a lot of that essentially verbatim using MPI for Pi. It also provides mechanisms for serializing, so pickling basically Python objects and passing them around. It's not as efficient, but in terms of developer productivity, it's quite efficient, right? And that's something we also want to keep a focus on. Like your time is not, it's not worthless. Your time is valuable, okay? I'm going to demonstrate that I have MPI for Pi installed. See, my ZSH autocomplete is like giving away all my spoilers. Let's see, I was doing something. I'm not going to do that though. And I do that by typing import MPI for Pi in a Python interpreter. And it works. Okay. This is one process. I'm going to quit the Python interpreter again, start it up, and this time I'm going to say from MPI for Pi import all caps MPI. So you may have noticed it took slightly longer there because it's actually initializing the MPI interface. So this now is the MPI namespace that you would get inside a C program. Typically in C, it'll look like MPI world, something like that with that leading underscore. MPI for pi namespaces it so that it looks something like this. So if I do mpi.com_world, all caps, that's what it looks like in C, except in C, it's got that underscore. And this is now an object. It exposes a couple things like rank and size. Since I'm running this right here, it shows the size is 1 because there's only one MPI task. And the rank is 0 because it's a 0 indexed index into that size. What I'm going to do now is I'm going to vim hello MPI world.py. Up here at the top, I always do that wrong the first time. From MPI for pi, import MPI. And I'm going to say print hi there from mpi.com world.rank of mpi.com world.size. Now, for bonus points, you could do this with like F strings or something like that. But I'm just going to do it this way, set in my ways. Now, in another window, or if you're using a terminal multiplexer, another terminal, whatever, I'm going to type mpi run-np for Python hello MPI world. Oops, I need to activate my environment first. So there we go. It happily spits out hello there from each one of the 4 different MPI tasks. So if we wanted, we could do something like import glob.glob, LSP, do white data, YT sample. You don't have to do this part. This is just whatever. FNs. Something like this. I guess you can do all your stuff with this. Now, glob famously did not used to be sorted, so this might actually have an error in it. But you can access MPI for pi that way. And you can also do things with it. And I'm going to go here from, you don't have to do this part, from MPI for pi, import MPI. It has things in here like send. Oh, I guess it's all methods on the com world. And so it has operations like send, where you can send any object to another destination. You can have tags and whatnot. And you can use this in order to figure out what goes where and how to do parallel computing. I think it was a number of years ago, but I think the Gordon Bell Prize at supercomputing was won by a code that was that had its parallelism written in Python using MPI for pi. And the CFD solvers were somewhere lower level, something like that. The thing is, this can get reasonably obtuse if you're trying to implement really high level operations in it. So YT provides a couple interfaces to this. I'm going to do parallel objects. Okay. ideally, let's say that we had a set of objects. Let's say that we had an expensive function. You know what? Let's import time so that we can make it really expensive. Okay. So we've got an expensive function that we call on some value. Now this expensive function for our purposes just sleeps for 5 seconds. And then it returns the value times 2. But you could imagine that it's doing something more complicated, like, I don't know, maybe it's iterating to convergence on some Monte Carlo simulation or something like that. And let's say we had values equals np.random.random 20. I'm going to change this time.sleep to 1. Put it over. We could say for value in values, expensive function value. Now let's have our total. And we'll do total plus equals expensive function dot value. We can say print took our values and got total. Sorry, I got confused with my windows. So now if I run this, it goes through, gets all of them, and actually it's random, so it's gonna like give a different result every time. I'm gonna quick change this to be linspace 0, 10, 10. And so it should take about 10 seconds. And it'll print out what it got. It got 100. So it summed up all the values times 2 and got that. Now I'm curious how long this actually takes. So let's go ahead and we'll say, and this is how I always do things, T1 equals time.time. And then at the bottom, T2 equals time.time. Right now, I think Clement is seeing how I'm writing this string. Yeah, he's covering his eyes. All right, I will do this the proper way with an F here. Took me T2 minus T1, 0.3 F. There we go. Is that better? So it should take just over 10 seconds, like incrementally more than 10 seconds. Yeah. But now let's say that we had 2 processors that we wanted to throw this at. If I just do MPI run -np2 Python parallel objects, what do we think is going to happen? How long is it going to take?
Same amount of time.
Yeah. That's a trick. It's going to take the same amount of time, but it's going to print it out twice. Oh gosh, it took 1,000th of a second less. That's disconcerting. YT provides a number of different functions that allow us to iterate over these things a little bit differently. In fact, the first thing that it provides is what's called parallel objects. Earlier today, Britton showed you p-iter on the time series objects. That's a special case version of this. Now, I'm intentionally showing you the wrong way to do this. But if I type now, having done parallel objects, and I run Python with MPI run, it actually does not change anything. It still takes the same amount of time because we need to enable parallelism. So it used to be that YT would like do its best to figure out, am I being run in parallel? Am I? And then it would, enable it and whatnot. We don't do that anymore. You have to explicitly tell YT, go ahead and be in parallel. And so we do YT.enable parallelism. And now when we MPI run, we get something a little different. So we got the correct slowdown in time. And in fact, it should scale. We do this, it should only take 2.5 seconds. I guess it took 3 seconds. Wow, sublinear scaling on a simple loop. But what's happening is it doesn't have a mechanism for automatically updating all of our values. Okay. Parallel objects, though, if we were doing something like now plot.save. So if I'm iterating over a time series and I didn't need to do any reductions at the very end, this would be sufficient. However, we can now construct a storage object. Oh, shoot. I always get this backwards. Yeah, okay. And we provide a storage object to it. So I'll say my storage. And as long as that's a dictionary, it's fine. And now what we get is we iterate over this and it returns to us a storage value and a value. It has special characteristics on it. You can set a result ID. In this case, we'll just set to be the value. And you can set a result. And when you come out of this, get rid of our other prints. This will be shared amongst all of the processors. There will be, and here, I just realized I did that. Sorry about that. I had a plus equals, but that value wasn't initialized, so it failed. So now let's look at this. We now have MP float 64 keyed to float 64.0. Each one of these is the result of all of our individual computations, and it is shared across both processors. If I don't set result ID, does it set one automatically?
Defaults to like the integers counter.
Let's do that. Yeah. It doesn't. Oh, no, it does, but it's in a different order. So the same set of values are now shared across all the processors. And it's keyed up so that each one can then query whatever the results are. And so if I wanted to do my total here, I could do sum storage dot values. Let's get rid of that printing of our dictionary. Oh, sorry, I keep like zooming in and out and I'm going too fast. I will work on that. What happened here?
Should be my storage.
Yes. Thank you. Thank you. My storage. So now we're once again back at having it scale and give us the correct answer. So those of you that have seen things like MapReduce before, this is basically MapReduce. Okay, it's a pretty straightforward way of doing that. We've and this the vanilla usage of parallel objects assumes an even workload distribution. But it has a ton of other options for it in case you need to do something more complex. So a couple things. You can also specify the number of jobs that it should execute. And I'll show what that does in just a second because it's really neat. You can also say whether there should be a barrier at the end, which in some cases you don't need, but in general, it's helpful. And you can also have dynamic allocation of tasks. Dynamic allocation of tasks is pretty neat. And let me see if I can demonstrate that. So what we'll do is we will say time.sleep mpi.com world.rank +1. Okay. So that means processor 0 is going to take less time to execute each task than processor 1.
It's for MPI.
Right. And yeah, thank you.
Too late.
It is too late.
Why do we need to do that?
Because
Right.
I'm outside the YT bounds right now. I'm like way off the map.
Add a core.
Yeah. So one of the cores will always be dedicated to dynamic process control, but it should be underutilized. So you should just always be able to increment it by 1. So here I'm doing MPI run 3. Took extra long, but we got the same results. No, we didn't. Say that again?
I mean, the total should be 100.
Yeah, we did not get that. Got the same. It's identical across all of them. Interesting. Oh, dynamic doesn't, dynamic has an issue with storage, I think. I'll deal with that.
Works.
I mean, it gives me the wrong answer though.
It's the same because the print statement is outside of.
That must be it. Okay. I'm gonna quick try this out. All right, we can edit this for time later.
Use IT my log info. You show the rank.
I'm right. Three, 6, 7, 8, 9, 10. Okay, I am almost certainly doing something wrong on this, and I will deal with that later. But you can see that here with the dynamic storage, it does, or with dynamic allocation, it does redistribute them as they go. The other thing that you can do, and let's go back here to dynamic equals false. You can specify the number of jobs that you want it to do. So let's say n jobs equals 2. And now if I do MPI run dash NP8, what ends up happening, and you'll see this, is that value gets distributed such that there are 2 total jobs, okay? It sets up multiple levels of parallelism in the hierarchy. So the top level of parallelism is the parallel objects. And in that level, it has 2 sets, because I said 2 jobs. And so it takes the 8 MPI tasks that are available and distributes into 2 different sets those jobs. Okay. So the top level would be just 2. And the next level down will be, oh, right. And it's going to take way longer because I've got this time.sleep in there. The next level down, there will be 4 tasks associated with each job. Okay. So once again, we get this. And because it's assigning to each one, it's going to get the correct answer. Because it'll overwrite the values. Oh, that's why it's doing it. With the dynamic, with dynamic equals true, the result ID needs to be explicit. That's what it is. So here, it takes way less time, although it shouldn't. Oh no, it should because I got rid of the sleep. And it gets 100, but each one of these is subdivided into groups of 4. What that means is that if we have an YT enable logging, what's the set log level? Set logging level? 0. 50? 0. Okay. Let's make sure that that does it. You'll see what ends up happening here, and I will hold off. I guess 0 does not work. Is it 10? Yeah. 10? It's gotta be a string.
Oh, it can be a.
Meant to be readable.
Maintaining this.
That must not be a function. It is log level. You'll see what it does. It sets up our individual objects. And then here, with parallelism enabled, it shows which task each item comes from. So let's take a look at how that works with iterating over data sets. Just realized I don't have could never get the data sets to download. And so tiny cosmology.
I have it.
Yeah. Okay. Oh, you know what? I think I might have it too. Or I'll tiny cosmology I can get relieved. Sorry, folks. I'm a little bit spacey today. You probably knew that.
Can I ask a quick question?
Please, you can take how about a question that lasts at least 2 minutes and 28 seconds?
Okay, just in this, we have, for example, a NVI string that actually the string want everything, but how they save the data in my storage?
It's a great question. So my storage has to be initialized. That way it's accessible outside of this loop. Like parallel objects can't construct something like that for us that exists outside the loop. So I create a dictionary. And then when I supply a storage, I change what I iterate over because it provides to me an object at each one. And so this could be storage result ID. I could set for if I want to change the key. Otherwise, it will be the integer index into the iteration. And then I say storage.result equals new value. So here, if I wanted to, I could say MPI comworld.rank, comma, I. Like this. And now when I do it, it will have my storage will have key values that are unique to the rank and the iteration. So one thing to note about this now is if I run this with n jobs equals 2 on more than 2 MPI tasks, it will no longer have the right result. It will be doubled up because if it will be doubled up by whatever factor more than 2 I have tasks. Because now I'm storing MPI comworld, so 0, 1, 0, 0, 0, 1, 0, 2, but I'm also storing 1, 0, 1, 1, 1, 2. So this is all the multi-level parallelism. Slowed down. Let me see if I can demonstrate that. I'm going to give myself a little more real estate space. And actually, let's go ahead and I will demonstrate for you parallel profiles. So I promised that I would describe the way that operations happen in parallel in YT. So let's say that we have our data set, and we'll do isolated galaxy until tiny cosmology downloads. And we load it, and we say profile on ds.r. And this is, you didn't go over all the different quantities mappings, did you? So we're going to say profile. And I want to profile along density with temperature, with a weight of mass. It should default to weighting of mass.
No weighting.
It should. I thought it would default to weight. Unless it's cell mass. So it did that. And now if I look at it, it looks like this. And in theory, for a small data set like this, it doesn't really need parallelism. However, we can enable parallelism and let's see, there may be, just because it's so small, there may not be any change here. But we can now run it, say, 2 processors. Let's see, it may actually just be completely the same because it's such a small data set. Probably limited by IO. It's even worse. Yeah. So with bigger data sets, it works a little bit better. But I'll describe to you exactly why something like profile should work better in parallel. So there are some operations that can be done in any order. So for instance, summing things up, if you already know the mechanism by which you're summing them, right? Because addition is nominally commutative, we can do that in any order. Even for weighted averages, as long as we track the numerator and the denominator separately, we can construct a parallel decomposition. YT has a notion of what are called chunks of data. So what happens inside the profile call is it chunks our data set. Now, for some operations, those chunks are spatial, but in others, it knows enough through the front end to identify the most efficient mechanism for IO chunking. Okay, so I'll give you an example. The process of reading a data set in HDF5 has a couple different bottlenecks. Okay, so ENSO is built on HDF5, isolated galaxy is ENSO. The same thing applies for Gadget and Eagles, and in a different way for Ramses. But the process of reading an HDF5 file involves opening the HDF5 file, parsing the metadata, whatever it is, figuring out where the different chunks exist on disk. If it's a, widely distributed with a chunking scheme, it has to figure all that out. But then there's a series of telling the disk to move to a different location, reading a stream of bytes, and then doing the next thing. Okay. Every time you open a new data set in HDF5, there's a small amount of latency that's associated with that. And so if you're skipping all over the different files, it can be problematic. It can cause real slowdowns. On parallel file systems like Lustre, this used to be a real big problem. I think it's gotten moderately better, but the process of seeking within a file was and opening a new file, so getting the handle on the file, so all this stuff like added up like something. And so what YT does is it figures out what data it needs to read, and it sorts it based on, say, which file it's in, where it's located on disk. It tries to avoid a lot of different seeks inside things like Gadget. I don't know to what extent it does this with Ramses, but in Gadget binary, it sorts it so that it can do it one big long read and not have to stop. And with ENSO, it does something similar. What YT does is then it distributes those chunks to different processors so that it can minimize the amount of memory that they each need to allocate to do their analysis, and also minimize the churn that they have in interacting with the file system. So this profile call internally chunks up the data set, distributes those chunks so that they are best balanced as it can. And then there is a final reduction operation where for this particular thing, it stores the numerator, the denominator, and then it does the division at the end. Okay. For some things, that's pretty straightforward to do, like profiles. 1, 2, 3. I think we just have 1, 2, and 3-dimensional profiles, but you could do n-dimensional profiles. That's actually really easy. For other operations, like computing the min and the max of a data set, it's also pretty straightforward. For some things, like the median, it's not, right? Like a running median is really tricky to do. There are ways of doing it, like median of medians and things like that. But if you want an exact median, it's not fun or easy or something. I don't know, or maybe it is now. But there are some operations that are good and some that are harder. One of the specifically difficult operations is the projection. Okay, and it's not intractable, but it is more difficult. So if I were to do something like s.r integrate density axis equals z dot plot dot save. Now this also adds a bunch of latency because each one is going to save the plot out, and so we get a big constant offset to all of these. To our scaling, it's like whatever the time is spent inside the projection plus whatever time is required to do the matplotlib save. So maybe I'll just do this. What YT does for grid data sets is it decomposes it in index space, and it constructs the final resolution projection because that requires reading no additional data. It constructs the data structure for the final resolution projection. And I'll explain what that, I'll explain in just a second about that. And then over the course of the chunking, it fills in that data structure. So when we do something like this, it has associated with it a set of fields, but it also has associated with it a set of pixel coordinates. These pixel coordinates are the final resolution. And this is why if you project once, you can plot many times, because what it has is it has a variable resolution result that it then just fills in inside your fixed resolution buffers. When we project in parallel, it constructs this component without touching the disk on every processor. And then it divides up the data set. Each one reads just its portion, and then there's a final summation across all of them. There is a mode where you can have it do a reduction, but it's generally speaking much only useful when you have memory limiting data sets. Okay. All right. So I have now, so the things that work nicely, profiles work great. Projections work all right. Slices are not the best because in general, it's very hard to find a distribution of work for slices that is gives the processor something to do. So I think that I have now successfully downloaded Enzo Tiny Cosmology. We can return to applying multi-level parallelism on that. So we can import YT, we enable parallelism. And if we do, TS equals YT.load, Enzo Tiny Cosmology, DD star, or I guess 4 question marks, right? We could do YT.parallel objects on TS, but as Britton said, it loads it normally. Let's do our storage equals that. or we'll call this my storage. And so now for storage data set in ts.piter, storage equals my storage. We can do multi-level parallelism. If we just do this, one task per data set will be issued. So we could do something like ds.r min density MA equals ds.r max density. Storage.result equals MI MA. Now let's import matplotlib.pyplot. This PLT. And I know this is duplicating some of the stuff that Britton showed. PLT.scatter. Here, let's unpack the whole thing. Storage dot result ID equals ds dot current redshift. Sure. Yeah. Z equals np dot array my storage dot keys. Mi equals np dot ma equals np dot array my storage dot values. Do a scatter of mi ma with that. Now, if we run this, MPI run np-2 Python parallel cosmology. It's splitting it up into sets of 2 jobs each. And we should get a scatter plot. Now, if I'd done plot, it would be bad because then it'd be all out of order and zigging and zagging all over the place. I guess I have to make it into a list because it's a key view and a value view. Fortunately, we won't be able to tell anything because it's in linear space that it's going to plot them. That's the problem. Avery, when you asked me yesterday, did you import NumPy? It cursed me.
Are those numbers with the slash showing which run it's importing each processor?
Unfortunately, no. So this,
Seem a bit random.
yeah, so what those are actually the grid counts. And so for really large simulations, it can take a while to do, does it save fig? When did you figure that out? Like just now or when I typed it?
I'm thinking about it.
So this, for really large simulations, oftentimes the parsing of the hierarchy can take a while. And so we put a progress bar on there. So what it does is every grid that it parses for Enzo, but here, because it's apparently able to do 15,000 a second, it's just going, super fast and it doesn't matter. You're probably put a lower bound on, a lower bound on the number you need for the progress bar. So otherwise, oh yeah.
In this case, do the scatter, PLT scatter one twice?
Say that,
I mean, the PLT dot scatter, PLT dot Y scatter, blah, blah, blah.
Yeah.
They went twice, right?
it'll happen on every processor. I'll show you how to avoid that in just a moment.
Okay.
Yep. Okay, so now let's try something slightly different. We'll do n jobs equals 2. So now if I do 4 here, and let's see if I can do set log level debug. Debug. Oh. It doesn't support end jobs. I thought it did. Oh, here, we'll do parallel objects on TS.
IT done.
Thank you. Oh, boy. I forgot why we don't set log level to debug. We'll try info. It was reporting the success and failure of every derived field. A lot of them. Yes. So check this out. Only the root of each set of jobs is reporting some of these things. So what's happening is I ran it on either 4 or 8, I forget. It is dividing it into 2, and then within each one of those, it's allocating it's allocating whatever is left to parallel iterate over the chunks. So what this gets us to is if you have the ability to run on like 1,000 processors and you have fairly large jobs or fairly large data sets, you could iterate over them and say you want, let's say you had, you've got 1,000 processors and you've got 100 data sets. You could say, I want n jobs equals 10. It'll then allocate 100 processors to each data set. Okay. And then within each data set, if they are of suitable size, this can be productive because it will then distribute it. Derived quantities in general are completely parallel. So doing something like min density, max density, mean profile, all of those things will distribute efficiently across processors. Now, you had asked, how do we keep it from happening on every processor? Is root, right? Yeah. So if YT is root, print, I am saving your plot. Now here, we'll do this without that. If 1, it would print it on every single one, right? But here, if we do if YT is root, it should only print it once, and it will also avoid race conditions. Now, mind you, there are cases where, like, if you have an early termination, it can kill your MPI job. So I think we barrier that is root by default. Don't we? Maybe that's only on root. Do we barrier only on root?
Probably,
Wait, what? I thought I had another 2 hours. Okay, so it only did it on one processor. It still looks good. Is it really time to go? Time to be done?
about 10 minutes ago.
Are you serious? Yeah. Okay, so that's parallelism.
One super quick question.
Okay, Britton, can I take this? Yeah. This
No, this one.
code.
But it's a stupid question.
It's not a stupid question.
MPI strings see my storage, and actually they are the same after the forward.
Which, sorry, This will be the same across all processors.
Okay.
Yes. Yes. I'm sorry for taking too long.
Okay.
Right, thanks, Matt.